Well, good evening. Tonight we're going to explore the third major section of our trilogy, which explores the advances in science and scientific understanding and their biblical relevance. Some of you may have seen our little package called Beyond Coincidence, which talks about the anthropic principle and how so much of a universe as we look around appears to be designed specially for us. You may recall in that when you look at the size of our planet, it turns out it's at the geometric mean between an atom and the universe as a whole. It's kind of interesting, a geometric mean. Between the atom and the universe, you come out with our planet. If you take the geometric mean of an atom and our planet, you come out to the size of man. So we've talked in our earlier sessions about the universe and the stars and the galaxies. And we've also talked a little bit about the solar system and the planet. Tonight we're going to go to the other extreme. We're going to go not only just to the atomic world, but deeper than that, we're going into the subatomic world and discover a science, an understanding that lies at the heart of almost everything in our life. One of the things that you may recall from our Beyond Time and Space package, where we explored Einstein's theory of relativity and its biblical implications, there was a Hebrew scholar. He lived from about 1194 to 1270. In other words, nominally the 13th century. Rabbi Moses ben Nachman, or Nachmanides as he's commonly known. He was the leading Talmudic scholar in the Middle Ages in Spain. Quoting from a commentary 600 years earlier than he lived, he made some interesting insights from Genesis chapter 1, verse 5, where it speaks of the first day, or more precisely, day one. From the Hebrew construction, he concluded that time did not exist prior to that verse. Now that's a tremendous insight. The concept that time could exist or not exist itself stretches our imagination, but it's interesting that Nachmanides, in his commentary on the Torah, makes that remark. That's something that most people had no ability to grasp until Dr. Einstein. Will come to that a little later. There was another Hebrew sage, very well known among Jewish scholars, by the name of Maimonides, a different guy, also about the same time, a little earlier. He and Nachmanides both concluded that prior to the creation, space did not exist. Now most of us, if we imagine the creation or the Big Bang or what have you, we sort of visualize something filling space. Something that you and I probably can't really grasp unless we've been specially trained, is that at the creation, space and time began. In other words, our universe is finite, but outside the universe is not empty space. There is no outside to our universe. And both Nachmanides and Maimonides, these two Hebrew sages of the 13th century, you'll find that in their writings from their studies of Genesis chapter 1. This is sort of by way of review because we touched upon this in our earlier session. I mention this because these Hebrew sages also made another observation that is absolutely staggering, but I'm going to come to that later. We also talked before about the expanding universe. This whole idea that the universe is expanding is a commonly held scientific view. And the rate of its expansion, there's mathematics are involved. If it expands forever, it's considered mathematically open. If it's going to expand and collapse again, it's mathematically closed. Now it's interesting, if it expands at a rate that will never stop nor close, that's considered mathematically flat. It's interesting, they've now measured it, and that's exactly the rate it appears to be operating. But what's interesting, that means it was tuned to 1 part in 10 to the 60th. If you can picture 10 with 60 zeros after it, 1 part, that's a gigantic number. It's tuned that accurately. Now what makes that interesting is that in physics, physicists generally consider anything that has a likelihood of less than 1 part in 10 to the 50th as absurd. So it is by definition, by their own definitions, absurd to consider that tuning of the universe as a happenstance or by accident. It implies a tuning. But one of the things I want to get into is most people have been taught that the universe is expanding because as the scientists observe stars, they are shifted to the red. The so-called red shift. The spectra of stars are shifted to the red. They call that the red shift. It's generally believed that's because they are rushing away from us due to a phenomenon similar to a Doppler effect. Just like a siren, when it leaves you, as it goes by, it changes its pitch, because when it's coming at you, it's higher. When it goes away from you, it lowers its pitch. That's called the Doppler effect. They've assumed that that's exactly what happens with light. And they even call this Hubble's law, the Hubble telescope in space. It's named after Edwin Hubble, who first postulated the Hubble's law, the idea that stars are rushing away from us, and you can measure their rate that they're rushing away by the red shift and also distance from us. There happens to be some problems with that no one wants to talk about. Halton Arp, an American based in Germany, has been studying discrepant red shifts. You notice that some of the shifts aren't to the red, they're to the blue. They're coming at us, not away from us. And that sort of has a problem with that theory. In fact, Andromeda, all of you have probably heard, if you're in astronomy at all, heard about Andromeda. It's rushing towards us. But there is an astronomer in the University of Arizona by the name of William Tift, who has discovered something even more disturbing. He spent 20 years collecting data, and he's discovered that the red shifts do not occur at random intervals. They occur in discrete amounts. In other words, they're quantized. And that happens to shatter the idea of the expanding universe, as at least it may be expanding, but it's not. That doesn't prove it. In fact, strangely enough, for some non-obvious reasons, the quantization of the redshift is one of the supporting discoveries that seems to support Barry Setterfield's conjectures that the speed of light's been slowing down. By slowing down, it affects atomic behavior, and that would cause the redshifts. But this is sort of by way of review, except it leads to an issue that we left in an earlier discussion, and that is this whole idea of the universe. As they measure it, they know its mass, but they discover something very disturbing. Over 90% of the mass of the universe has yet to be discovered. All the stars and all the galaxies and all the material that astronomers have been able to identify accounts for something less than 5% of the mass of the universe. So they believe there must be gigantic amounts of mass that we don't see yet. They call this dark matter. In other words, it's not luminous enough to be seen in a telescope. But that's an enormous problem, and there are all kinds of searches and investigations chasing this idea of cold, dark matter. And there are all kinds of theories about this. It's interesting, just as a beginning, let's turn to Genesis chapter 1, which of course has the famed creation account in the Torah, the first book of Moses. Picking it up about verse 3, and God said, let there be light. I don't think it has anything to do with the lightning outside, but who knows. And God said, let there be light, and there was light. And God saw the light, and it was good. And God divided the light from the darkness. And God called the light day, and the darkness he called night, and the evening and the morning were the first day. And God said, let there be a firmament in the midst of the waters, and let it divide the waters from the waters. And God made the firmament and divided the waters which were under the firmament from the waters that were above the firmament, and it was so. And God called the firmament heaven, and the evening and the morning were the second day. What does that mean? Who knows? All kinds of commentaries in Genesis may take slightly different views about this, but I want to point out to you that what he's talking about, the word firmament there, and waters, may not mean what you and I think of as H2O or that kind of water. Most of us have been taught in our high school physics that there are three states of matter: solid, liquid, and gas. When you get to college, you discover there's a fourth state of matter, and the fourth state of matter is the most prevalent one, namely called plasma, dissociated atoms. And exactly what is referred to in Genesis chapter 1, verse 6, 7, 8 will be different if you read a classical commentator, or rather than if you read the writings of, say, someone like Dr. Jerry Schroeder, who's a nuclear physicist and also an Orthodox Jew, who would relate this very quickly to cosmological issues that are now well understood. But I move on to talk about plasma, as it might be alluded to here in Genesis 1, because you and I are going to move tonight into a realm that has a lot of surprises for us. But before we do, turn to Hebrews chapter 11. And I'd like to just remind ourselves of the first three verses of Hebrews 11. Hebrews 11, verse 1, now faith is the substance of things hoped for, the evidence of things not seen, for by it the elders received witness. Verse 3, through faith we understand that the worlds were framed by the word of God, so that things which are seen were not made of things which do appear. Now that can mean many things. You can take that very casually, or you can also take it very, very denotatively. We now know that the world, in fact, is made of atoms. The atoms are made of particles that are smaller than light itself, so they physically can't be seen. And that's rather provocative. Most of you, when you were in school, probably had some exposure to a model of the atom. Most of us have visualized the atom as a nucleus around which is an electron. Now, the atom is about 10 to the minus 8 centimeters. The nucleus is about 10 to the minus 13. And the ratio is the interesting thing. In other words, the nucleus is 100,000 times smaller than the atom. If you want to make a model of the atom and we made the nucleus a pinhead, then the electron would be 100 meters away. In other words, an atom is essentially nothing. It's mostly empty. If you want to make a ratio of the volume of the nucleus against the volume of the atom, remember now in volume you go length, width, and height, so it's a cube relationship. If it's a 10 to the 5th relationship, but you cube that, you're suddenly at 10 to the 15th. In other words, if you take a volume of 10 to the 15th units, the nucleus is one part in that. To give you a ratio of how big 10 to the 15th is, if I take the age of the universe as 10 billion years, you're talking like, what's 1 minute to the age of the universe? That's the ratio of the nucleus to the size of the atom. So the first thing we begin to sense, despite our convenient little models, is the atom is mostly empty space. The actual substance there is amazingly small. We'll get back at that in a minute. But what we're going to do tonight is explore a field of science that is a gigantic paradox. Most of us in this room have heard about Einstein's theory of relativity, but probably aren't impacted by it day by day, except philosophically. And there are many, many advances in science that we probably may know about, but impact us every day. The advance in science that impacts us more than any other happens to be a field called quantum physics. And what's interesting about quantum physics, first of all, it underpins all other sciences. Without quantum physics, you not only wouldn't have lasers, you wouldn't have integrated circuits. We're all familiar with computers and semiconductors and microcircuits. You look at one of these little microcircuits, in 1 square inch, you could have over 3.1 million transistors. If you're building one and there's something wrong with it, you can't look at it through a microscope. It ain't good enough. Your standard tool down the hall is a scanning electron microscope because the circuit elements are smaller than light itself. And that's the kind of technology you and I have now grown to take for granted. Now, we could talk about semiconductors and computers. The other area is DNA. We've all been aware of the incredible advances in microbiology, molecular biology, genetic engineering. All these fields depend on a science called quantum mechanics or quantum physics or the quantum sciences. Now, this is a part that may surprise you. There is probably no one in the world that understands it. There are many people that know how it works, that apply it mathematically, apply the recipes because they work. And yet, as you try to understand it, you discover that the implications of how it works are so staggering that Ludwig Boltzmann committed suicide trying to wrestle with it. And you'll discover, most of you may have heard of Niels Bohr. We speak of the Bohr model of the atom. He lived from 1885 to about 1962. His famous quote was, "Anyone that is not shocked by quantum physics has not understood it." Because the implications we're going to get into are staggering. And we're going to be moving into tonight a world that is self-contradictory. We're going to move into a world where scientists now have discovered that nothing is real as you and I would think of reality. We discover we cannot say anything about something when we're not actually looking at it. Nothing is real unless it's being observed. Now, when I say that to you and I in our world, that's absurd. But when we move into the quantum world, that's the way it works. We're going to be moving into a world where self-contradictory statements can both be true. We're going to move into a world that has denied causality, We're used to science where something is always caused by something else, not in quantum physics. We're going to discover it's not determinate, it's probabilistic in some very strange ways. But the staggering discovery that we're going to explore a little bit is that reality is not local. If you take two photons that are speeding away from each other at the speed of light, measurement in one immediately affects the other one instantaneously. They're somehow connected. The particles seem to be inseparably connected to an indivisible whole. They apparently are aware what's happening to the other one. And we now discover that every particle in the universe apparently is immediately connected. It's as if they can communicate instantaneously, not at the speed of light, much faster. And the implications of that are staggering. Now, the first thing that we discover as we get into this world is we wonder, why do they call it quantum physics? Because we discover everything is quantized. For example, if I took a ruler, no matter what length it is, I could cut it in half. If it's a foot, I can make a 6-inch rule out of it, right? If I take the 6-inch rule, I can divide it in half, make it 3 inches. No matter what length I have, you and I would conclude I can always cut it in half. No matter how small it gets, I can always divide whatever it is by 2. It turns out that's not true. It turns out there is a length. Smaller than that doesn't exist. Not only of length, but of mass and of energy, and most amazingly of all, time. There is no unit of time smaller than 10 to the minus 43 seconds. Now that's very small, but the bizarre thing that we have a tough time getting an intellectual grasp of is, why can't it be smaller? We discover that length, mass, energy, everything in the universe is quantized, comes in specific units. It's digital, not analog. It consists, in effect, of symbols rather than actual quantities. And that's going to have some very surprising implications for us. We're going to talk a little bit as we go. If you're in this field, you'll hear a term called Planck's constant. Max Planck was a physicist. He postulated a constant that turns out to be very, very critical. What's interesting about the constant, it's in 4 dimensions. And we're going to get into this dimensionality here in a minute. But at this point, maybe what I really should do is back up a little bit and just give you a quick overview of atomic physics. The term atom, of course, came from the Greek because they conceived Democritus of Abdera and Epicurus of Samos. This is about the 4th century before Christ. Lucretius Carus of Rome. They visualized that the universe was made of little tiny particles. And they postulated the smallest thing that can't be divided, they called an atom. And that's where that term really comes from. And as you move, of course, nothing really got discovered significant until about the 17th century, when Robert Boyle and Newton and all those guys redeveloped the roots of chemistry in the 17th century. About later in the 18th century, Frenchman Antoine Lavoisier discovered why things burn and oxygen and all that. In early 19th century, John Dalton started developing the atomic concepts of matter, molecules of chemistry and all that starts to show up. Joseph Guy Lussac, simple proportions and gas combinations. The Italian Avogadro in 1811, his hypothesis was a big one. And so it turns out that chemistry really had its day. By the time you get to the 1890s, something else starts to take over. Chemistry is taken over rather dramatically by events in the physics world. A Scotsman by the name of James Clerk Maxwell and an Austrian by the name of Ludwig Boltzmann introduced the concepts of entry in thermodynamics and so forth. It was about 1895 that Röntgen discovers X-rays, radioactivity and all that starts to develop. The big thing happened with J.J. Thomson. He developed at the Cavendish Laboratory, which was originally established by Maxwell in Cambridge. He discovers the electron, and that leads to all kinds of things. That brings us about to the turn of the century. And the guy that, of course, impacts everybody is a guy by the name of Albert Einstein. He had a life of failures and disappointments. His elementary school teachers described him as a foolish dreamer and asked him to drop out of school because he just didn't pack the gear. He had very few friends in school. He didn't get a high school diploma, couldn't cut it. Had to retake the exams for college. He failed the exam for the Swiss military, had flat feet. After graduation, couldn't get a job. So he's rejected everywhere. He eked out a living for a while as a tutor. He was about 21 at the turn of the century, about 1900. He finally got a job as a Swiss patent office clerk. And because that clerk's job wasn't very demanding, he had time to pursue his interest in physics. and he published on Max Planck in 1904, which led to a revival of the corpuscle theory of light. I'll come back to that in a minute. But in 1905, Albert Einstein publishes 3 articles. First was on a special theory of relativity, the E equal mc squared business. You've all heard about that. But he also published a paper on the reality of atoms. It was his paper that established the reality that atoms were real by Brownian movement and so forth, a famous paper. But he also published a third paper which dealt with the interaction of light with electrons. And that was the first work dealing with quantum mechanics, for which he got a Nobel Prize in 1921. Now, what makes this ironic is the whole area of quantum physics was started by Einstein's paper. And yet, as it develops, Einstein could not buy the conclusions it was leading to. And he went to his grave believing that quantum physics was somehow wrong because the implications of the experimental evidence was, as you'll see, very disturbing. Let's just take a quick look at the atom we had before. The Bohr model of the atom is the one that most of us have been taught. We've been taught that there's a nucleus and around which travel electrons. And depending on how many electrons and what the composition of the nucleus determines what material we're talking about. We generally see the simplest atom as hydrogen, which has a proton in the nucleus and it has an electron orbiting around it. This is in the classical rendering. All these models, by the way, are wrong. They're just convenient to try to help visualize things. The helium, if you add a few, so you have 2 protons and 2 neutrons. And because you got 2 protons that's positively charged, you then have 2 electrons, you then have the helium atom. As you build up the nucleus, you're building up the electrons, you start building the various elements which are, of course, familiar to us in the periodic table. Lithium and carbon being examples here. Give me the next one. This happens to be an atom of methane, but it demonstrates how molecules appear to form. At certain energy levels, the atoms seem to be stable if there are 2 electrons at that energy level. Well, the carbon atom is short. It turns out if you take 4 hydrogen atoms, they can share electrons so that each hydrogen atom feels that its shell is complete, and yet the carbon atom also feels that its shell is complete. By sharing those electrons is the classical way most of us have been taught, valence or molecular combination in chemistry. But again, our mental model has always been analogous to the solar system, where you have a nucleus around which orbit these electrons, something like planets. And that's convenient in high school physics. It's also convenient in a lot of ways to visualize it. But it turns out what we're really going to end up dealing with here is something that isn't visualizable. So I mention this just by way of familiarity, and yet at the same time we're going to discover as we get into this that first of all, these are not the basic particles. That we start looking at these particles, we've got bigger problems. Give me the first chart. It turns out there are about 200 particles. And I thought we'd go through each one and all its characteristics this evening. And of course I'm being facetious. But there's a group of particles that are called fermions that are what you and I would consider material. And these particular particles obey a certain kind of mathematics, the Fermi-Dirac statistics. But the main point is there are things called hadrons, and there's a whole family of these things. Baryons that are protons, neutrons, mesons. The neutrons are highly unstable. They have a half-life of about 11 minutes. So neutrons are very unstable. Protons, on the other hand, are stable for like 10 to the 30th years. So as we start studying these particles, we discover they have all kinds of attributes that can be measured and inferred. And I won't take you through those, because first of all, there's most of those that look unfamiliar. They're the safe ones. The ones that seem like when they talk about spin, they don't mean spin or isotropic spin like you and I would think of it. What you need to recognize is that these attributes of these particles are arbitrarily named, and in some cases named whimsically. But they are determinable, measurable, repeatable. So out of this you get a whole alphabet soup of the hadrons. Let's move on to the next one, next chart. I just want you to be aware of these as we get into some other things here. They also have leptons. These things come in flavors. For each of these particles, each one also has an antiparticle, a particle that's the exact opposite of it. And that's going to be important to us a little bit later. Another class of particle are quarks. They come in about 6 flavors. Up, down, charm, strange, top, bottom, truth, beauty. They also come in 3 colors. red, blue, green. Now, what you need to understand, if you can do any reading here, all of these labels are whimsical. They actually talk about quantum chromodynamics. A study of this would be called quantum chromodynamics, after the so-called colors. They're not colors like you and I would think of colors, because again, colors have to do with light. We're smaller, not only smaller than light, we're smaller than the nucleus of an atom. These are the elements that make up the protons and the neutrons, which make up the nucleus of the atom. I call them pigments of your imagination, actually. Now, they have not been directly observed, but the evidence of them has been measured. So you're in a very, very strange world here. Now, generally, when you take a particle and its antiparticle, they will collide and mutually annihilate themselves, throwing off a photon. The photons are very strange particles. I've left them to last because they're the ones that are going to create most of the problems for us. Photons are the unit particle that make up light. Photons have no mass. They're always in motion at a speed typically called c, or the speed of light. Each photon is its own antiparticle, which leads to some interesting equations. There's a whole other family of particles that are the mechanism by which forces are exerted in this world. There are basically 4 forces in the universe. Gravity, which I think most of us think we understand. Electromagnetic forces. Then there's 2 kinds of atomic forces, a weak and a strong force. That's the way they're called. But these 4 forces explain everything observed throughout the universe. 4 forces. Electromagnetic is perhaps the most dominant in our thinking. It's about 10 to the 36 times stronger than gravitational forces, to take the 2 extremes. Now, what I'm trying to spare you is getting you a whole history of how these particles were discovered and how they measure them. They're very exotic, and it's been quite a quest with multi-billion-dollar atom smashers for years to discover these particles. But you'll also discover that the more they learn about the particles, the more questions it raises. I couldn't resist introducing at this point in a technical lecture a poem that I think applies. If you start reading in this area, I think you'll remember this poem. It's called The Blind Men and the Elephant. You probably read it as a child. It was 6 men of Hindustan, to learning much inclined, went to see the elephant, though all of them were blind, that each by observation might satisfy his mind. The first approached the elephant, and happening to fall against his broad and sturdy side, at once began to bawl, "God bless me, but the elephant is nothing but a wall." The second, feeling of the tusk, cried, "Ho, what have we here, so very round, so smooth and sharp? To me 'tis mighty clear, this wonder of an elephant is very like a spear." The third approached the animal, and happening to take the squirming trunk within his hands, thus boldly up and spake, "I see," quoth he, "the elephant is very like a snake." The fourth reached out his eager hand and felt about the knee. "What most this wondrous beast is like is mighty plain," quoth he, "'tis clear enough the elephant is very like a tree." The fifth, who chanced to touch the ear, said, "Even the blindest man can tell what this resembles most. Deny the fact who can, this marvel of an elephant is very like a fan." The sixth no sooner had begun about the beast to grope, than seizing on the swinging tail that fell within his scope, "I see," quoth he, "the elephant is very like a rope." So these men of Hindustan disputed loud and long, each in his own opinion exceeding stiff and strong. Though each was partly in the right, they all were in the wrong. So oft in quantum physics wars, the disputants, I ween, rail on in utter ignorance of what each other mean, and prate about an elephant not one of them has seen. So as you read about the quarks and the muons and the neutrinos, it's interesting because as they search these things, they can obviously do repeatable experiments to identify them, and yet the more they learn about them, the more disturbing qualities emerge. Now I want to focus on the principal one. The question, the central paradox of quantum physics is, do these particles act like particles, or do they act like waves? You say, well, that sounds pretty simple. You should understand that in the days of Isaac Newton, he viewed light as a stream of particles. We call them today photons. But it was interesting that about 1629, born in 1629, Christian Huygens developed the wave theory of light. Refraction, reflection of light, but the corpuscular theory of light is still preferred. There was a mathematician by the name of Euler, if you like. He's the guy who invented geometry, trig, calculus, pi, the square root of -1, I, integration, and so forth. He and also Ben Franklin were both ignored until 2 developments occurred in the 19th century. Thomas Young, an Englishman, conducted a two-slit experiment which demonstrated the interference of light. And I'll come back to that in a little bit. Which demonstrates that light behaves wave-like. It has behavior that implies it's like waves, like radio waves or something. Now, Newton was knighted in 1705. He died in 1727. That's just about 2 years before Young developed this. It was still too early to dethrone the British idol. But Fresnel, a Frenchman, about the time of the Napoleonic Wars, he did a more complete study, and noticing the color of light when it hits an oil film, the refraction, and the diffraction, the interference, again, he concluded that light acts like waves. Behind him comes Leon Foucault, a French physicist, who established the speed of light was less in water than in air, which was no surprise from wave theory, but makes no sense from a corpuscular theory. You start thinking that through, and it doesn't make sense. Then along comes James Clerk Maxwell, a Scotsman, who established the existence of waves which involved electric and magnetic fields, and Heinrich Hertz in 1887 established electromagnetic transmission reception, which we, of course, know as radio. But it's interesting, by the end of the 19th century, the whole thing switches. Only a genius or a fool would suggest that light is corpuscular. They bought totally the wave theory of light. I say a genius or a fool at the end of the 19th century. Who comes along at the end of the 19th century? A guy by the name of Albert Einstein again. And he publishes on Planck and so forth. Now at this point I've got to introduce a guy by the name of Max Planck. One of the problems physicists were dealing with about the turn of the century was trying to develop the mathematics that would account for black body radiation. When heat would radiate from what they call a black body, an object, it had some properties that defied being defined mathematically. And Max Planck, in struggling with this, trying to find an equation that would explain the problem, he combined two different mathematics, the Rayleigh-Jeans law for long wavelengths and the Willem-Wien laws for the short wavelengths, and he misapplied the mathematics out of desperation and discovered it worked if he misapplied it. And Einstein's later work explained why it worked, but he actually made a mistake, and out of that mistake the thing all worked. The mistake he made is he didn't integrate properly. If all these properties were continuous, you would integrate in calculus, but they weren't, they were discrete. He didn't integrate, and it worked. The reason it worked is because they were discrete and they wouldn't be integrated that way. The point is he made a mistake, unknowingly stumbled on the fact that energy is available only in finite discrete lumps called quanta, and that's why you don't integrate it, and it was not infinitely divisible. He developed a constant that relates all this called Planck's constant. It's a basic thing in quantum physics. But the main point is it's four-dimensional, and Einstein picks up on that. Now, I guess what we need to do at this point, I want to jump right in to the central paradox or mystery of quantum physics. The question that the physicists were struggling with: does light behave as particles or as waves? You say, well, that's kind of silly. There are conditions in which it operates as particles, photons. Light behaves as if it's a stream of particles called photons. Under other conditions, light acts as waves. That's what gives you prisms, diffraction gratings, etc. It turns out, as they try to wrestle with the nature of light, they discover some strange things. Let's hit the first slide there and see what I've got here. If you take a shield and put a tiny slit in it that's small compared to the wavelength of the energy that's behind it, it will act as a source of that energy. And as you could expect, the distribution of that energy on a detector or a screen or what have you on the right would be primarily in the axis of that slit with some splatter on both sides. If you were aiming like machine gun bullets, a bullet at a time, you would expect it to hit mostly in the center and maybe for whatever reason splatter around that a little bit. We can relate to that. It acts like a particle. Give me the next slide. If we put next to that single slit a shield with two slits, and that energy comes from the slit to the next two slits, each of those two slits will act like a source of that energy and then will distribute itself on the shield or detector. Now here's where it gets a little more complicated. Imagine in the second slit there I close one of those slits. Or if I open either one at a time, I would get one of those two humps you see in the middle. In other words, if I close the upper slit, I would have just the bottom little distribution. If I close the other one, opposite. In other words, each slit acting independently will give me the distribution in the middle. The intensity of the reception there would be the square of each of those energies. In this case, h squared plus j squared will give me the intensity that I will expect to see. But if I have them both open at the same time, the energy acts like a wave. They will interfere with each other. They'll reinforce some places, cancel other places, and I get a distribution that looks something like we have on the right there. The equation h plus j squared is h squared plus j squared plus another thing. It's no longer just h squared plus j squared. There's another term, the 2hj term, if you know your algebra. In other words, if it's acting like a wave, I get that equation. I get interference bands. If it's acting like particles, I just get h squared plus j squared. So you say to yourself, okay, if light is going to behave like particles, it'll behave the one way. If it's going to behave like waves, it'll behave another way, that are distinctly different when you measure them and follow a different mathematics. That sounds pretty good. Well, got to back up a little bit. Let's just hold this for a minute. Along comes a guy by the name of Heisenberg, Werner Heisenberg, and he developed some mathematics that have been widely misunderstood and misquoted because they're known as the uncertainty principle. It turns out that the theoretical models for particles, whether you're talking light or electrons or subatomic particles, they all behave like particles in some occasions and waves like another occasion. And these two descriptions are complementary. But it turns out that it's impossible to measure precisely complementary pairs of measures. Typically, for an example, if you're talking about an electron, you'd like to know its position and its momentum simultaneously. It turns out you can't get them both simultaneously. The more you know about position, the less you know about momentum. The more you know about momentum, the less in other words, you have to trade it off. The uncertainty that you're stuck with is always something larger than Planck's constant divided by 2 pi. And I won't go into the mathematics why that's true. The point is, there is a number, it has to do with Planck's constant, that you can never reduce the uncertainty to or below. That's Heisenberg's uncertainty principle. Now, when physicists first saw that come out of the mathematics, they felt that was a comment on their experimental skills. No, it's intrinsic in the design. So they started to say, gee, we should be able to determine when an electron is acting like a particle and when it's acting like a wave. So they started to devise all kinds of clever experiments in which, for example, if one of the two slits is closed, it behaves like a particle. If both slits are open, it behaves like a wave. But as they started to study that, they discovered something very disturbing. If I take a single electron, and I'm using electron, it could be a photon, they actually use other particles for other reasons, but the point is, as it comes out of that slit, if the other slit is open at that instant, it behaves like a wave. If that slit is closed, it behaves like a particle. And what bothers them is, how does it know? In other words, I'm talking about the other slit. It turns out, as they start chasing this, it's as if the electrons know what they're trying to measure and always behaves the other way. And as they started doing that, obviously that doesn't make sense. But in the particle world, again and again and again, that was confirmed. It is so ridiculous, logically, that a guy by the name of Schrödinger, about 1935, to try to dramatize how absurd that is, he created an example, rhetorically. He says, imagine that you have a box, and inside the box you've got a cat. The box is fitted with a shutter that can detect a subatomic particle, and if it detects that particle, it will break a vial of cyanide and kill the cat. What he imagines is to take this box and put it in a circumstance, so you can't predict a particle, you can only predict its probability. But we create an experiment where there's a 50-50 chance that a particle will hit the shutter, which will break the cyanide, which will kill the cat. Now the question is, let's assume that that's open for a certain interval of time t. So you open it for that interval of time t when there's a 50-50 chance a particle hit it or not. The question is the cat live or dead? It's inside the box, you can't see. Now, once you peek in, you can see whether the cat's alive or dead. In the field of quantum physics, the position is that cat is neither alive nor dead until you look. And that's ridiculous. And that's why Schrödinger developed this example to demonstrate how ridiculous the conclusions they were coming to were. The only way they could describe this is that once they make the measurement, what they run into is what's called the collapse of the wave function. The wave function is there until you try to measure it. And that, for reasons that no one can figure out, is called the Copenhagen interpretation of quantum physics. It's got nothing to do with Copenhagen. None of the people involved were in Copenhagen. But somehow that label got to that view. But the main point is that there is no reality except while it's being observed in the quantum world. Furthermore, every particle knows what is happening to every other particle. So the only way a particle can behave like a wave is if there's other particles involved. And as they try to isolate that, it behaves contrary-wise. Now this, of course, strikes at our very concepts of reality, that nothing is real. And as one said, we seem to be living within just a consistent delusion. And this is why Niels Bohr said, anyone who is not shocked by quantum theory has not understood it. The more you understand, I'm just giving you some examples, but the central thing you'll read about if you read in this area is the two-slit experiment, which almost everything comes back to this kind of a thing. Now, a guy by the name of John S. Bell, working at the European Research Center, CERN in Switzerland, near Geneva, in 1964 devised an approach using proton spin, and I won't go through the technicalities of it, to resolve the puzzle. And he based it on three basic things: that there are real things that exist, regardless of whether or not we observe them. That's what we'd figure, right? That makes sense. Secondly, that it's legitimate to draw general conclusions from consistent observations on experiments. And third, that no influence can propagate faster than the speed of light. Basic tenets of physics, three basic things. They call this local reality. Well, he developed the mathematics to approach this experiment. In 1972 at the University of California at Berkeley, they started some experiments. By 1975, 6 such tests were run. Of the first 7 tests that were run, 5 of them violated the Bell inequality, as it's called, thus demonstrating that a local, realistic view of the universe is false. In 1976, at the Saclay Nuclear Research Center in France, they spent a fortune trying to demonstrate the Bell inequality with their atom smashers and so forth. And again, they get the disturbing proof that local, realistic views of the world are false. In 1982, at the University of Paris South, a guy by the name of Alan Aspect, you may hear about the Aspect experiment, that happened to be his name. Again, quantum theory is established, and in fact the theory was the experiments were so thorough and so well done that it seems to have laid it to rest. Now what this ends up meaning among people who are in quantum physics is that everything in the universe is immediately connected to everything else. There's some of these scientists that believe that every proton is connected with every other proton. Every electron is connected somehow with every other electron. Nothing is certain. This is all probabilistic. The most prominent name in recent times in quantum physics is Richard Feynman, who is at Caltech. And we'll talk about him in the next session a little bit. I think his quote, I love his quote, he says, "I think it is safe to say that no one understands quantum mechanics. In fact, it is often stated that of all the theories proposed in this century, the silliest is quantum theory. Some say the only thing that quantum theory has going for it is, in fact, that it is unquestionably correct." So the latest experiments prove that there's no underlying reality to the world. Every particle seems to be inseparably connected to some indivisible whole, each seemingly aware of what happens to the others. Now this concept, getting back to the cat, is the cat alive or dead before you look? Quantum physics clearly demonstrates it's neither until you look. And that leads to some non sequiturs in our world. There are some scientists that hold the view, that the way they try to visualize reality is that there are many universes, and when you look, you pick the one that you're going to be in. The concept, the many worlds concept. So they try to reconcile the concept of reality with multiple worlds, with lots of both dead and live cats that are selected when observed. And each universe is unaware of the others. Now, Stephen Hawking believes you get wormholes between those universes, and that's another whole thing. But to these kinds of people, then, where they're surrounded by ghost worlds, that will never be experienced. This is very popular with science fiction writers, but hardly satisfying to you and I. So to summarize where we are, science finds itself at the very boundaries of reality. It deals in units of length, mass, and time that cannot be further divided. They're digital, not analog. They're alphabets of symbols, not continuous. Science now deals with events that are not caused, they follow probability distributions. Causality, which is the traditional handmaiden of science, with its attendant certainties, is now a thing of the naive past. There is no causality anymore. That's the whole fountainhead that the science was built on, is that one thing causes another, not in quantum physics. So physics, which traditionally has been the most rigorous of the sciences, is now cast adrift on a sea of uncertainty. Now it's kind of interesting to me, because when we speak of uncertainty statistically, go to the Scripture says the lot is in the lap of the Lord. When we look at these particle lists that we saw, there are the gluons. These are the things that presumably hold the atom together. Turn to Colossians chapter 1. Let's start about verse 16. It says, by him were all things created. Who's it talking about? Huh? Jesus Christ. By him were all things created that are in heaven, that are in the earth, that visible and invisible, whether they be thrones or dominions or principalities or powers, all things were created by him and for him. And verse 17 is an interesting verse. And he is before all things, and by him, your King James says, all things consist. What it actually says is, by him, all things are held together. We've taken a rather clumsy, superficial summary of the beginnings of quantum mechanics to discover that it's at a dead end. It has gotten to the very boundary of reality. They are at a point where they cannot rationalize what they know. The question is, are there other dimensions to consider? And we have some surprising insights that have developed that we'll take up in the next session.